to this student-run panel for the CNST Nanotechnology Workshop. My name is Josh Lloyd. I'm on the student panel. These are my two colleagues, Adrian and Katrina. I'm currently a fourth-year graduate student in the Department of Electrical and Computer Engineering. I'm working with Professors Joe Lighting and Eric Pop. Specifically, I'm looking at transferring and growing graphene to arbitrary surfaces. And Adrian, what do you do?
My name is Adrian Nocha. I'm a first-year material science student working with Professor Lighting. I work on trying to make atomically precise nanostructures using tips and probes.
Katrina?
Hi, I'm Katrina Keller. I'm a first-year student in bioengineering. I work with Dr. Rashid Bashir, and we're working on using MEMS devices to explore biophysical properties of cells.
All right, great. So at this point, I'd like to ask our distinguished panel to go ahead and introduce themselves and their respective backgrounds, starting with Professor Leggett on the far right.
Yes, I'm Tony Leggett. I'm in the Department of Physics. My interests are mainly in what's normally called condensed matter physics and quantum information. So I guess my prime contacts with engineering and nanotechnology would be through some work I've done on quantum dissipation and also my interest in quantum computing.
Hello, my name is Ben Barbieri. I'm the president of ISS. ISS is a local company, and we make fluorescence instrumentation, fluorometers, spectropluorometers, confocal microscopy. We also have another product line, tissue, it is more biomedical, using near-infrared light to measure properties of the tissues. We are based in Interstate Research Park. We are local here.
Hi, so I'm Lloyd Whitman from the NIST Center for Nanoscale Science and Technology, where I'm the Deputy Director, and my interests are in nanotechnology and nanotechnology policy. And prior to my current position, I had, for a long time, I was a group leader at the Naval Research Laboratory doing everything from semiconductor nanoscience to biosensor system.
Hello, my name is Akinwande. I'm a program manager at DARPA in the Microsystems Technology Office. And that office tends to do a lot of electronic systems that are usually based on nano and microsystems. And we have a lot of nano electromechanical and micro electromechanical systems. I manage a number of programs that have nano embedded in them and use nano to improve performance and push the boundary. My daytime job, no, my nighttime job is teach at MIT, and I'm in the Microsystems Technology Lab, where we do a lot of nano-related stuff. But I also chair the IEEE Electron Device Society Nanotechnology Committee.
My name is Piotr. I'm with National Cancer Institute in Bethesda, and I oversee a large program that is dedicated to the use of nanotechnology in different oncological applications, with particular emphasis on cancers which have a low probability of survival, ovarian, pancreatic, lung, and brain, and we're looking both at diagnostics and therapeutic applications. In the past, I worked in semiconductor materials and also have done very good work in microfluidics for sample preparation for genetic analysis.
All right, great. So with that, now that we all kind of know where we stand, I think I'll open the questions with the following question. Panelists, which experiences have influenced you to choose your current career? As graduate students, what advice do you have to give us as we consider future career paths? So, Professor Leggett,
Okay. Well, I can't actually say it was any particular experience as such that caused me to choose my current career. I wasn't the kind of person who sort of takes apart a radio to find out how it works. If I had, I wouldn't have been able to put it back together again, I suspect. And in fact, I had essentially no interest in science of any kind during my high school career. It was only towards the end of my first degree in Oxford, which was actually in the humanities, that I gradually came to realise that maybe I would be interested in thinking hard about the natural world. And I think what particularly attracted me about physics, the idea of doing physics, I had essentially no experience on it, but the idea that attracted me was that you could make non-trivial predictions about the way the world works, and hopefully you or your experimental colleagues could get out there and prove them true or false. Since I had already done one degree in the humanities at the British taxpayer's expense, I had considerable difficulty persuading anyone to consider me seriously for a second undergraduate degree in physics. But very luckily, I had a lot of people on my side and in my corner, and I did in fact eventually succeed in persuading them, and then went on to a career in physics in more or less the standard way. So I think what I would say to you is, if you somehow feel in your bones that there is something that you would like to study, or some career that you would like to choose, then try to move heaven and earth to achieve that. I think it would be worthwhile to do so.
It's very interesting, Professor Leggett's experience. I have a more prosaic background. I also come from physics, but laser spectroscopy. And yes, I did start working in a laboratory at the university, just doing atomic spectroscopy. And then little by little I moved towards building instrumentation. And yes, for some reason I had this passion about instruments, about gadgets, and this is what I'm still doing today. So yes, I definitely would agree with Professor Leggett. If there is something that you would like to do, try to push hard and follow your instincts.
So I actually did have a pretty singular defining about experience, which is, so I was a physics major as an undergrad, and it was something very complicated, which is I wanted to figure out how to get a job for the summer. And I grew up in New Jersey, not far from where Bell Labs was, though I didn't really know anything about Bell Labs at the time. This is back when it was a thriving place. But I did know that one of my professors had a one-time work there because it was written in a little blurb from the brochure from the physics department. So I went up to him one day and I said, "Do you know if they ever hire somebody, like a college student for the summer?" He said, "I think they might." So I ended up getting a job with one of his former graduate students who was a new hire there, and doing surface physics related work, and that just, that was like, wow, this is amazing. It was really interesting, and that essentially defined my path for a long time. But I would offer the following piece of advice: is that I think it's always good to have some direction that you're going in. Maybe you're heading to Chicago, but at some point you shouldn't be afraid if something really interesting happens that, you go to Cincinnati or something. But the point is, at some point you need to recognize that when you reach a certain level of competence as a scientist, you've got a postdoc or you're doing your research, you will not be afraid to go in different directions, because I went in many different directions because it looked interesting. And I didn't necessarily know where I was going to go, but I knew I had a connection. I could take a connection from my existing expertise and build it in that way, and use all of the same tools and sort of intellectual methods that I had done in my first work to go into a wholly new direction. So you shouldn't necessarily be confined that this is what I did for my PhD, therefore I will do, this is the only thing I will ever do, and not be afraid to go off in different directions. I think almost everyone on the panel has some experience. Piotr certainly another case for that, as you saw in his talk. So that would be my grand wisdom that I can offer.
Yeah, second, a lot of what has been said, but my background was that I have a traditional electrical engineering background. Went through school with most of that, but I was always interested in physics along the way. So most times I would take classes across some would be in electrical engineering, but also would take almost the same topic, but do it in physics, and kind of see the difference in the world. But when I got to grad school, I really wanted to do communications and information theory. And that's what I went to grad school to do. But then I got into one class, and the professor was so good in explaining what the world was all about. And I said, okay, maybe I should try something different from information theory. And so I started working, with the whole idea of microfabrication and device fabrication at that time. And it was a particularly poignant time in Silicon Valley in terms of all the activities that were going on there. And then I went to industry. And by the time I went to industry, I decided that I wanted to get away from to do other semiconductor materials but stay in the same area. But after while in industries, by some coincidence, the company that I was working on at that time, Honeywell, they had a sudden challenge from one competitor, and they decided they needed my expertise and I should abandon. But I was able to get a good deal for myself in terms of negotiating what else I'll be working on if I finish up the project. And so, yeah, it was one of those things that I was able to do a lot of what I wanted to do, even though the company had its own set of priorities. I was able to balance both of them. And it was then that led me back into academia. So my current position as a DARPA program manager came mostly as an outgrowth of my work in academia. But it's also been a lot of what you bring in your vision of what you want to create, and then you go create it. So that's been a lot of fun. It's a lot of trying to think of what you want to do and trying to get to it. It may not be immediate, but it will come down the line.
So when I was in high school and then later in college, I really liked to solve analytical problems. That seemed interesting to, think the process through and trying to figure out and get to the bottom of these things. That seemed natural to continue then to graduate school and getting a science degree. In college, actually, I was studying systems in electrical engineering. I was good at math and physics in high school, so that seemed like a natural. And I wasn't particularly crazy about that. But I finished college degree. Another thing I really liked in college was skiing, but they didn't offer a degree in that, so I continued with electrical engineering. When I came to graduate school, I actually started to look at materials, mostly for electronic and optical applications. That seemed much more to my liking as compared to what I'd done in college. So I guess, sometimes you know exactly what you want to do from the very beginning. Now, in other cases, you probably need to go through a few different iterations and try different things. And I stuck with that and then moved, as Lloyd was also describing in his case, to very different areas which I didn't anticipate really to look at when I was in graduate school. That happened 10 years later, and I didn't really have any specific background to go there, but I guess the interest of the company and my personal interests were structured in such a way that I enjoyed that. I think another issue is, one is to show the interest in science and pursue it, then another thing is what you do in science and what environment you work in, because you can do a lot of different things. You can be a faculty, you can work in the industry, you can start a company, and do many other things. So I think that's another factor in addition to deciding to be or stay in science. And that, again, probably is quite difficult to determine without really trying it. Now I think, each of you who are about to graduate in the near future will have not only several jobs, but several careers. So I think the world is changing in such a way that now you will be doing naturally more different things, spanning across more different disciplines potentially. So in a way, that can potentially provide opportunity to try a lot of different things and see where you do the best.
Thank you for that.
So now that you've told us a little bit about the past and what you see for our future, I'd like you to try to answer what you personally think is the most revolutionary contribution that nanoscience and nanotechnology will have in 2020, 2050, 2100. It's a tough question.
2100?
Yeah.
Will everybody?
That's right.
Any of you?
Well, life expectancy will be 120.
All the Peter's therapeutics are going to keep us alive.
And so we'll start with Professor Leggett and work our way down again.
Okay. Well, I think in the nature of things, it's really pretty much impossible to foresee what developments nanoscience and nanotechnology are going to bring us over the next 100 years. But for what it's worth, I think my best guesses are that by 2020, there will have been really dramatic developments in the use of nanotechnology for medical purposes. That is, for example, for attaching small magnetic particles to proteins which will search out particular bits of you that need healing and so on and so forth, and can then be manipulated. My impression is that there have been enormous advances in this area in the last 10 years or so, and that this is likely to continue, and I think even by 2020, this may be something which is in some sense installed in every hospital. 2050, well, again, iffy, but I think there's a reasonable chance that a quantum computer may be built at the level where it actually is useful for something. Right now, we believe that we understand the basic principles of quantum computing, but the actual the devices which have been built are really, in some ways, pretty rudimentary. I mean, they can, for example, tell you that most likely the factors of 15 are 3 and 5, but they don't go an awful lot beyond that right now. I believe that there's a reasonable chance that by 2050 they will have got to the stage where they can perform certain tasks like factoring fairly large numbers in a way that will be competitive with classical computing. More excitingly, I suspect that, I hope, that we will have thought up all sorts of qualitatively new things that quantum computers may be able to do that classical computers simply can't. And not just they can do things faster, they can do qualitatively different kinds of things. 2100, well, I think there's a small chance, perhaps I wouldn't like to put a number on it, but that we will be getting to the point where we can actually start seeing quantum mechanical effects at the level of, for example, the human visual system. We're actually starting right now an experiment which is a very small step along that direction in the physics department here at the University of Illinois. I think it's very unlikely, in fact, that this is going to produce anything dramatic, but I think by the year 2100, people may have got far enough along that road, they can actually see these really weird and bizarre quantum mechanical effects coming up at a level which is, in some sense, rather uncomfortably close to human consciousness. So those would be my best bets, but I really wouldn't like to put a lot of money on any of them, frankly.
I see a lot of improvements in devices that have medical applications. There are already groups out there that are trying to experiment with CCD, tiny CCD implants in the eyes, and this is interesting for people who don't have eyesight. And so this is where nanotechnology is an example of the application of nanotechnology, and there are several that will actually help in improving the quality of life of people who have some sort of impairments. In terms of consumer, I think the biggest, the largest difference will be that we will see more and more deployment of sensors at different levels. It can be the sensor in our homes for the refrigerator or the heating, but it can also be the sensors in the cars. And I think that if not by 2020 or by 2050, we might have cars that are just driven by robots, so that we don't need to take care of the cars. And who knows, maybe we will reduce the accidents on the way. In terms of more vision, long-term vision, I think that the computer, even the standard computer, will change a lot. Of course, now we have the iPad, which are less than half an inch in thickness. But I think that little by little we will see screens that we can actually carry and that we can actually fold, like materials of some sort, and maybe that we can buy instead of fabric. So we can go to the Joanne fabric store and just say, oh, give me 2 square yards, and then now I come with that screen, I put it up, and I have sensors in the building, I connect to a computer, and right away I see my poster, or I can click and I can bring up a presentation that I have stored somewhere in the clouds. So this is what I might see, or what I would like to see. It's funny because recently I was having dinner with a friend of mine, and his daughter Katie was there. At a certain point, Katie said, oh, I just need to call my friend, and she made this sign. And I said, well, that's interesting. In my times, we didn't know about this sign. I used to do this sign, this symbol. So yes, technology and the world changes a lot, even in a relatively short time.
I think there's a broad consensus here. I'll mention one of the material in the short term that hasn't been mentioned, which for Nano was actually instructional materials, which is probably, other than healthcare applications, the nearest, I think, commercial, that you're really going to see in the commercial space. So, for example, we have some interactions with Lockheed Martin, who's doing a carbon nanotube-based composite material for an aircraft that they can make in one step, and that replaces something that was a laminar composite structure that took like 6 manufacturing steps to make, right? So and it has superior performance with much lower manufacturing costs. So I think you'll see a lot of that. So, but then in terms of the other time frames, I'm going to challenge the question. From Washington, you answer the question that you want to be asked, right? Asking that kind of question really shows the sort of immersion that you have as a graduate student, that nanotechnology is something people are going to still be discussing in 90 years. So I would argue that if nanotechnology is successful, even by 2050, no one will really talk about nanotechnology, just as we maybe don't talk about many other technologies that are just ubiquitously a part of what we do. And actually, if you think of one way to think about how about that question is, pretend it was 1924 and ask what would the question you would have asked then be about now? Because you certainly wouldn't have asked, you would have asked about something that we would now go, what, what is what are steam engines going to look like in 90, in 88 years? Where's it going to impact be? There's been huge, if you look at technological revolutions, the one thing about them is that they're usually unanticipated, right? So the whole semiconductor industry was unthinkable in 1924, right? And so I think it's, I think a better question would be to ask, what do we think are going to be the challenges facing the world in 90 years, and what technologies are going to be needed to fix them, rather than what nanotechnology is going to be doing then.
Well, I'm going to suggest that by 2020 we're going to reorganize the way we do computation to not be as deterministic as we do it now, but it will be a lot more powerful and use a lot less energy, and it will be taking advantage of the fact that when we can make things small, they get faster and they maybe use less energy. And it could be that, yes, we can go into more probabilistic type of computing because of the fact that the dimensions and the reproducibilities that we have are not what we can, or it may be a better way to organize the computational process itself. I think we're going to be able to take advantage of the promise of nano, simply the fact that you have a much larger surface to volume ratio, and that will allow you to maybe look at sensing in different ways. And the challenges that we still have, how do we interconnect them, how do we interrogate them, will spur us to think of novel ways to interrogate individual devices instead of trying to reach them the way we've traditionally done. So I see some room for a lot of things. What would that enable? Probably means that we will be able to do things in ways that are more compact than we can now, but also it could be a lot more that we do a lot more things remotely. So now to 2050. I think by that time we should be not talking about nano, we should be talking atomic scale things. So I expect that we'll be doing atomic. Well, somebody came up, I think part of the, I think not exactly part of the Zyvex UIUC program on the tips-based nanofabrication. But the whole idea was that you can do an atomic computer, essentially using a single atom, an atomic transistor, using a single atom as a three-terminal device. So the power of being able to do that, and what that entails, maybe it affects the way we do cryptography, or how does it impact security, for example, becomes interesting. And also, what does it do to our sensors and ability to use them in ways that allows us to remotely sense and remotely see what we cannot do today. And also, what impact will that have on our ability to, by atomic layer, layering of things, to build devices that will have much more functionality than we have today. And I will side with you in terms of 100 years time. I wouldn't know what exactly it would be, but I know the humans will still be here and will desire a lot of things, and it will be driven by what type of lifestyle they want to live, and what we do will derive from that. And I agree, it may not be called nanoscience at all, but it will be driven by new pursuits, essentially things that make our life easier.
Yeah. Speaking glasses can have its advantages or disadvantages. You may run out of things to say because everybody else already said that, or you can build and draw on what I have said before. So I think I'm glad that Professor Leggett thinks that there will be major need for nanotechnology and also breakthroughs in medical sciences. And I think definitely that's an area where you see very compelling impact. Right? I mean, if you can make people live longer or healthier, that's a very noble goal. So I think in a short period of time, a lot of the therapies I talked about in the morning will move forward, will get implemented. Probably there will be a number of different assays for cancer and other diseases, especially infectious diseases, which can be even administered home. So you will not need to go to the doctor to get the diagnosis. And of course, there are some ethical issues related to that, but for some diseases, probably it's worthwhile to implement something like that. Maybe drug delivery and maybe not delivery of drugs which need to be administered frequently, painkillers or others, can move again to more sophisticated implanted devices. And so that, I think, that can happen in 10 to 15 years, so maybe to 2020, maybe 2030. I think there is also another space which we didn't talk about, is using some of the complex materials which Lloyd mentioned for coatings and development of new prosthetic organs. That probably will move forward as well. From cancer standpoint, I hope that by 2050, this will become chronic disease which can be managed and people will live indefinitely. even if they have it, and hopefully by 2100, will be clever enough preventing it or developing vaccines against it that will be almost able to eradicate it.
Thank you very much. I guess only time will tell. So for this next question, we're going to mix it up a little bit and start with you, Dr. Grodzinski, and give you a chance to answer first. We hope this question gets a little bit heated, actually. Out of the major research thrusts, being energy, bio, and computing, which is the most important and why? Oh, I'm sorry. Well, yes, go ahead. Sorry.
Yes, I'm sorry. So you want me to ask the last question, not number 3?
Yes, number 5.
Right. I'm not really sure that I could identify any one of these 3 as more important. They're all clearly extremely important. I would think the one, in some sense, which has the most chance of making a radical change in the way we see the world is the computing side. And in particular, sorry if I sound like a scratched record, but I would think that if real progress is made in quantum computing over the next few decades, that really is likely to change the way we see the world and our relationship to it. But as I say, I really don't think one can sensibly identify any one of the 3 as obviously more important than the other 2.
I would agree with that assessment. It's just not easy for me to say which one would take an important aspect over the other ones. For once, of course, energy is very, very important because the population increases, everybody needs to have access to energy. The bio part is also important because of the quality of life, improvements of quality of life. And really, nothing can proceed, can make a quantum leap unless the computing comes in and really helps in solving some of the problems that we're facing.
Well, so why don't you go next, and we'll go this way. So we can.
That's fine. So no, I think I will agree with 2 previous speakers that it's really difficult to say which one is important. Most important, I think it's important to know what's the definition of the important before you answer the question. Because if you look at if importance is how dramatically life can change because of the given contribution, then maybe computing. Or maybe even energy. But if you talk about improvement of quality of life and health of people on the planet, then obviously bio aspect will play the most significant role. So again, for instance, if you look at the comparison of medicine and electronics, let's say, in the last 50 years, the way we do medicine really didn't change that dramatically. But things which we can now do thanks to electronics, probably nobody could even predict 50 years ago. I mean, 50 years ago we barely had integrated circuits. So I don't think anybody could think about the internet revolution at the time. So in a way, some things will have more impact, but on the other hand, some other things may be more important to sustain life on Earth. So in my view, there is no compelling answer here, or singular answer.
So maybe I should go next.
Yeah, sure.
Well, I look at the way computing is done today. It's really not used for computing. It's used for information transfer. Not only that, social media and social networks has taken over far abroad. So it's something that is human in us. We want to interact with each other. It's part of what we call a quality of life. And to the extent that we have gizmos, gadgets, or better means of being able to interact with each other, I think those things will proliferate as much as they can. But there's also the reason why we want to live forever. And so, but that also plays into what I say quality of life, maybe not as much into our social interactions, which to collectively as a society tends to determine how we live. I'm not equating the computing to social life, but I'm saying it helps in terms of ability to communicate. I would say that I remember 30 years ago when I got to the US, and if I needed to call to Nigeria, it was about $5 a minute. Today it's 1 cent. So life is so much simpler. So I think all of them will push forward, but I see that looming challenge of how much energy we have if everybody uses energy at the same rate. So we have to generate energy, but also we have to be more cognizant of how we use energy in efficient ways. So each one of them will drive innovations that will allow us as a whole to, and each one of them will have to use some kind of nanoscience or some kind of science that is related to nano that will be enabled by nano. I see that energy maybe to reduce the amount of energy we use to do a particular thing, or to either move places or to send information across places. But I also see it helping us to a large extent. So I'm not going to pick any winners. I'll say, but to the extent that we will be able to collectively use it to move our societies, I would say those technologies will go along that.
I'll make trouble again. Right, so I can cynically look at this question and say, you're asking, did I pick the right area in graduate school, or which area should I go in as a postdoc? Right. But again, you think about, so the question is, which of these is more important, and then you'd have to say, more important to who? Right? Because you're going to get a very different answer. I mean, and I guess George Whiteside from Harvard talks a lot about science should not talk about the science, but talk about the problems that you're solving. And I'll come back to that because, if you're somebody somebody in some place in the world who has no health care and no energy and no water, you really don't really care so much about computing, right? But if you have pretty good health care and lots of energy and clean water, then, what device you're holding in your hand and how much computing power it has might be really important to you, right? So there's lots of elements to all these things, and if you look in the country as a priority, it tends to change based on external factors like the price of oil, which aren't controlled by the United States, but in other parts of the world where there's lots of oil, maybe energy research isn't so important, and they want to, so it depends on where you are and who you are and what you're trying to solve as to which one of those is going to be important. And it's not going to be a constant in any way. And in fact, in our country, it changes maybe every 4 years, which is more important.
Okay, so those are all very bureaucratic answers. That's fair. That's okay.
Healthcare.
Okay. But in that vein, can you say what policy changes, if any, we made to improve the funding process, specifically to incentivize good science? There's been a lot more cases of retraction, say, in scientific journals, a lot more data that's been fraudulent or plagiarized. So what sort of steps can be done, either from a funding process or in a bureaucracy process, to incentivize good science? Dr. Barbieri?
Well, I look at the problem more for my little corner, since I don't work in the academia.
Right.
I work in industry. What I can say is that in the past 20 years, 30 years, obviously there has been a fairly large investment in science. And here we have representatives from NIH or NSF. All of the federal agencies have been prolific, I would say, with money. And the Congress, apart from the ups and downs, the politics of the September, October, always gave funds to the agencies. From my standpoint, from my corner, as working in a company, there is a program that I took advantage of, and this is the SBIR program. We have grants from NIH and from the Department of Defense. And for me, this has been very important. We developed 2 instruments using those programs. And this is something I would encourage everybody who has an idea or like to start a company. every students to look into this type of program because they are great. I cannot say anything else about that. So I'm just glad that Congress passed the reappropriation for the SBIR grants and the program continues. So that I'm very grateful.
I'm trying to think of the coupling between improving the funding process and incentivizing good science. And what part of the funding process you're trying to improve. I think the beauty of science is it's a self-correcting process. I mean, even today. So there may be, there's always going to be people who do the wrong things or do stupid things. I'm not sure we're going to fix that. And hopefully what we really want to do is maintain a robust peer-reviewed system of where people keep doing that. I think there's a lot of interesting trends and if anything, actually, the sort of, social media kind of developments and how science moves into that area will probably make that even more open. That's a very interesting, there's probably many faculty here involved in trying to figure out, journal publishing and peer review and how that model moves forward into an age with where you want to do everything on a blog or a wiki, or there's a huge interest throughout the whole system, including in the government, and making data more readily accessible and making things happen, sort of by community. So those things actually, if anything, will make it much, much harder to sort of propagate any kind of scientific fraud because people will see it much, everything will be much more transparent. In terms of how to improve the funding process, that's another question of which agency and which funding process, and so it's the problems at NIH are probably very different than those at NSF and other agencies. So I think I'll pass on that one.
How to improve the funding process? I think there are several different models that exist now. The NIH process is different from what I call DoD processes, and even within the DoD, there are different funding models that are in there, and they're quite different from NSF, and each one brings something to the table. And so, thinking about how to improve it, I think improvement. I'm not, is the process broken? I don't think it's broken completely. And is the process working as it should to some extent? I think it's working to a large extent as it should. But there are improvements that could be made so that the process works a lot more seamlessly and the right set of people are rewarded. I think those are the things that we could, at least in the first degree, try to get moving. And so I'm not convinced that the process is broken enough to want to change it significantly. And I think there should still be different models, and each one should serve different communities or different stages of career could be served by each one of those processes. In terms of how to incentivize good behavior, I still believe the best way to do things is a peer review process, in which case the peers get to review the work and make a judgment about what it is. But there's always a chance there's a head mentality, everybody moving in the same direction, and there's this one person who says something nobody believes, but turns out to be right. And as long as that person has an audience, and I think this is where the social media could play a part in trying to at least provide such a person who is contrarian, but is not moving in the same direction, but he happens to be correct. At the end of the day, will still be heard, because there's a little bit of democratization of the process, but it should still be reviewed so that people consuming the material will know that it has been vetted in some way or the other. So that's my.
I should have recorded Beniamino's answer, because he said that government invested a lot of money into a number of different areas in the last 10 years, and SBIR project is great.
So I'll take that.
Exactly. Not that, you know, when you talk to people, a lot of them are upset about how hard it is to get funding today. So apparently not everywhere, and also perceptions are different. And I think part of the difference in perception may be that when you look at, yeah, it definitely is true that it's the pressures on funding system right now, government funding system in the US are much higher than they were before, and getting funding from government agencies is probably harder than it was before. But if you look at many other countries, not all countries in the world, but many countries, including European countries or Canada, the amount of funds which is available there for research is probably lower per capita than in this country still. So times like that probably will not last forever, and then the amount of funding in research will go up. Probably not happen next year, but eventually it will. So I think it is a combination of patience to go through that, and also looking at diversifying opportunity of where you draw money from. And I think that some disciplines are more prone to that than the others, but in addition to the government, there are philanthropic organizations, industry, and so forth. I think that, as Piotr said, I mean, people put a lot of thought into how to structure funding system and how to review the proposals. And there's no system which is perfect, but I think a lot of things are working reasonably well, except of course when the hit on proposals in single digits and reviewing, you know, selecting one proposal out of 10 or 12 is definitely hard. Now, in terms, there was also this issue of looking at publications which may not necessarily report on accurate data, and I agree with Lloyd. I mean, there's always sample apples, but I think science is actually probably more honest field than many others in life. So I think number of people who would consider doing things like that is probably still quite low. And I think that the more rules you create to trying to avoid things like that, the more, you know, more rules don't necessarily help. So I think the only way is to hope that people are honest enough, and that the field is competitive enough that basically things like that will be exposed if they do happen, and then people will ultimately probably do less.
Thank you. At this point, we'd now like to ask the audience if you have any questions, and they'd be happy to address them. Can you take this one?
Yeah.
Please.
We can just repeat the question.
You can just repeat the question.
Just give a question.
Anyone does have a question. Yes.
All right, so
Or
this
maybe-
might be a fun one, but
We like fun ones.
there are a lot of public misconceptions about nanotechnology and maybe just nanotechnology in general, but you know, you may have heard some of these like, oh, it's dangerous, or you know, it's all talk, it doesn't deliver, et cetera, et cetera, et cetera. What are some of the ones that you've heard out there, or that you see out there very commonly, and what can we do to try to combat these misconceptions?
Well, I think so. I don't know if there's a...
Anybody can take
You can
it.
go first. I'll go second. I have it.
I think that's often happening with new technologies. You know, there's still ongoing conversations. The cell phones can cause brain tumors, right? Even 20 years after we started to use them, and hopefully they don't. But so naturally, probably is fearful of things which they haven't dealt with in the past. Plus, they read Michael Crichton's books, and you know, they worry about nanobots. So I think what helps in situations like that is really educating society as a whole about science and making science more friendly to the society. And so any outreach to even K through 12 and younger people in general, at the same time, in our case, working with patient advocates, trying to talk to them about new technologies, or having open days for people from Urbana to come through the university and showing them things which you guys do. I think then activities like that break the barrier and suddenly make science feel more familiar. It's of course a slow process, but maybe next generation will be less concerned than the current generation of people. And I think also if technology delivers on some application and shows that really can do and perform the way nothing else performed that way before, then people will gradually start worrying about it.
Going to make a comment. So first, actually, the scientific community has some share of the blame for this problem. Right? So we can't go around, and I've been in this now for a long time. So we can't, on one hand, tout the great, amazing properties that you get by going to the nanoscale, and how they give you really unique things and really unique properties, and then turn around and say, oh, but they're just as safe as the larger quantities of those properties. Which a lot of people, so honestly, we need to take it quite seriously that, that we don't, there's many things we don't know. I mean, NIST is just starting a program looking at life cycle issues of what happens. We were talking about using carbon nanotubes in composite materials and structural materials, and people have to do the science and understand what's going to happen to these things in their life cycle, and understand what the risks are and what the health implications might be. And so that's one side of the equation. The other side of the equation is about hype, which is to everybody likes to sell their program, but I try not to roll my eyes too often when I see these press releases about something that was done, and you see it is so far from any actual practical use. But the last sentence of the press release is always, "This will revolutionize something sometime in the future," right? So we're going to be careful about overselling what we do. Now I will comment, Piotr and I are both involved in the federal government agencies that actually take this problem tremendously seriously. And there's a lot of really good people trying to figure out to do the right thing. And in the regulatory agencies like the FDA and the Consumer Product Safety Commission, those kind of places, are really, they're being criticized for being slow, but they're being slow because there's really an interest in the federal government in the U.S. to do science-based regulation. In other words, not to regulate things until you understand what the risks and the properties are. And there's a lot of programs going on in that space to do that. Now that actually poses, it turns out, a huge problem to businesses, because businesses face then huge uncertainty in their businesses because regulations haven't been set up. So it's actually a very, very complicated problem that affects a lot of people in a lot of ways. But again, I think as a community, the scientific side need to be very honest about both the potential good of what we do and also what we don't know about. We should never just off the cuff say, oh, you don't have to worry about that, unless you really know a lot about it and are sure that's the case.
I would just say openness is probably the best solution to all this. Just be completely open. I happen to work before in the city of Cambridge, and they came up with all kinds of ordinances, essentially that restricts all the things that can be done. And what it does is that it doesn't allow you to do the science so that you can allay the fears that are being generated. But I'm not saying that people should not, it's fear of the unknown, and it should be proportional to the threat it may pose or not pose. But a lot of like it has been said, it's really because there's a lot of overpromise, looking at the upside without acknowledging that there are enough things we do not know. But also, the case can be made that there are some risks, but the risks are unknown. As of now, this is what we know. And people can then make informed decisions based on. but we should not try to completely message it. Let them make their own decisions.
Okay, any other questions from the audience? Yes.
Yeah, I'm very happy that government, company, and universities are working together on nanotechnologies. And when we compare the nanotechnology, I totally agree with you that nanotechnology is not the purpose. The purpose is for the application. So for research the properties of the nano systems, like quantum solar cells, how do you compare how do you balance the properties research and the application research? So like we do the solar cell, quantum solar cells, people always compare the cost and efficiency with the normal solar cells, like silicon solar cells. So in your research, how do you balance investigate the properties of those nanosystems and the applications?
So you all got that question?
Yeah.
Okay.
Well, you want to start?
Yeah, I could start on this. Typically, I come from an organization which usually anytime you have a program, it's a portfolio of things. We do everything from basic to apply, and you try to bring everything to as much as possible that makes reasonable sense to the problem at hand. But the focus is always on the problem you're trying to solve. And so there is nothing that prevents you from having a group that is pushing the application as far as possible, but have another smaller group, maybe looking at the more basic side of things with the idea that will feed in sometimes in the future. They don't have to be the same performer, but it's a portfolio of solutions that you're looking at. So we have that luxury of being able to do that. And the question that comes up is how much money you have for which area. And that varies according to the specifics of the problem at hand. So the balancing act that you're trying to suggest is usually either resource limited or limited by the definition of the problem you're looking at and the urgency of the situation. So each one is a case-by-case basis that you make that decision, and you hope, and then you can redirect. There have been times whereby you started with something which is very applied. I'll give an example which happened originally when the chip-scale atomic clock was started. It was started by one of the systems offices, and they thought they would be using it within a short time. And then they ran into roadblocks. Then said, well, let's go do some of the science first. And that's how it then came back to one of the technology offices. And could you have decided right ahead that, okay, you should have done that first? Probably not. And you should still go in and figure out what the problems are. And it's only when the problems are clearly defined that you maybe decide which direction to take. I hope I gave you enough to chew on in terms of that it's never a clear-cut situation, but it's telling like the facts that are in front of you.
Yeah, no, I think that's exactly right, and both are equally important. And depending which environment you'll be working in, the emphasis will be more on one than the other. Obviously, industry focuses more on application, and often you can probably achieve the application without complete and fundamental understanding of the problem. On the other hand, at the university, you probably will have a tendency to work on both. But I think what is important to remember is that ultimately, very good understanding of fundamental science will help you in optimizing and improving your technology which goes into the application. So I think that's a fundamental issue, that if you don't spend enough time on the basic aspect, your device at the end probably will not work as well or as optimal.
Yeah, I'll add a couple of comments. So again, there's a couple of different factors that go into this, as alluded to. and some of it has to do with where you are and sort of what your purpose in doing whatever it is. So obviously, so for example, if your main focus or one of the important part of your job is training students, and frequently more fundamental work is fine, and you might not worry too much about the applications because that's serving that mission. Of course, it depends on who's paying for it. On the other end, it also has to do with your personal interest. Some people just really don't find to apply the application stuff of interest. And again, assuming one can be in a position or a place where the fundamental work is valued and you can find someone to pay for it, that's great. Right? Now, on the other hand, if you're really interested in actually applications, my suggestion is that you learn, even if you don't fully do, you're not going to make a flat panel display, a PV panel that's a meter by a meter, that you should learn about the business and the industry and the costs and the economics, so that at least you can address it sensibly to say, well, yes, if someone says, is this ever going to be viable, you can answer the question, or you can say, well, here are the challenges that would have to be overcome by someone, it might not be me, or here is a sort of a vision of how I think what would happen to make this scalable and economical, right? So then you can address that question. And honestly, on the other end of the extreme, if you're someone who really likes the applied work, I think it's important to recognize what the fundamental barriers are that someone else, if it's not you, should be worrying about that would help you. So just sort of have a picture and pick where you're going to be, and you might span the whole range, or you might just be in one part. It's really what you want to do.
Yeah, I would agree with this assessment. Is the fact that, of course, even if you push applications, you might finish up against a wall and then go back to study science. 10, 15 years ago, fluorescence was made with chemicals, probes that were attached to whatever, protein, DNA, and then we invented nanoparticles. Great, we can engineer the nanoparticles, select the excitation, the emission wavelengths. It seems like the perfect graph. Well, after a while, people discovered that there is some toxicity associated with that when you use them in cells. Well, great. Somebody went back to the table, to the drawing table, and said, well, maybe instead of nanoparticles, we can use tiny carbon particles, diamonds. And that started the whole field of science in the past 4 or 5 years. And that will give us a better understanding of the basic science, eventually a better application.
Thank you. More questions from the audience?
Could you share with us some critical challenges when you just started your career after graduation, and how did you solve them? Give us some inspiration.
So the question was, could you please share some critical challenges when you started your career, and how did you solve them? All right, anyone can start.
Well, when I graduated, I was hoping to stay in academia, work in the academia, so it's not that I got up one morning and decided to do what I'm doing today. It was just, I would say, a process, and I guess the challenges are the same challenges that everybody might meet in any type of job. If you work in the academia, you have challenges, of course, with your work, with your research, and then if you move on, they change as the conditions change.
I'm trying to pick which of my sad stories I should relate. So I originally applied to be a postdoc with someone at NIST, and between the time I actually went and visited, and I had another offer which I declined, and then I accepted, and then a few months later, the person, was a very, very famous guy at the time, called me up and said, well, I'm leaving for a faculty position. You should come anyway, because I have a hot new staff member that just hired you, should come work with him. So, so I went, and I literally, the day I was unpacking my books in the office, the new advisor said, well, I don't want to freak you out or anything, but I have an interview for a faculty position. and so that was in January, and then by July, he was gone. So, so somewhere in there, and then there was tremendous pressure on me to stay in the group and work for a third person in this particular place. But I actually knew someone, one of the people I work with now, actually Joe Strosho, someone from graduate school, And I went over and I actually did something that was very unusual in the institution, which is basically 10 months into my postdoc, I switched and started a whole nother postdoc, which was really challenging and then required a lot of begging and pleading to get an extension since I started late and everything. But you know, it all worked out. Basically, it all worked out great in the end. But I also, pursued other. I made sure I was aware of other. I didn't wait for someone to come rescue me. Let's put it that way. You want to make. If you run into a problem, I like to say you want to make your own luck. All right. People will look back and they'll say, "Oh, you were so lucky." But rarely is anybody really lucky. Usually the people who people think are lucky actually worked really hard to make sure they had the opportunities to end up where they were.
Well, I think Lloyd is right. So when I finished, my group was most of the people who were graduating from my research group were going to the industry. But I had an offer for a postdoc in Bell Labs. It was in early 90s, and Bell Labs was still very good place at that time, but I think there were some indications that it may be going down.
That's the one I turned down to go to NIST.
Okay, well,
it was a couple years earlier.
So I remember that I had an offer from the labs, and I was interviewing with a small company, and I kept delaying the acceptance with the labs to get the offer from the industry. I went to the small company gladly because the labs group, I think, a year later or 2 years later, got dissolved. So that was, I don't know, good intuition or lack. But of course, the company which I went to, I didn't read their financial sheet that well. So the company was actually more trouble than I thought. So 3 months later, I got a job at Motorola. So I was like one of their, so I didn't last there very long. So I moved twice within the span of 3 months. But when I got to the lab in Motorola, I stayed there for 10 years. So that was eventually good choice. But I think that's what it said. You need to anticipate things all the time. And Andy Grove, who was CEO of Intel, wrote a book called Only Paranoid Survive. So, certain level of paranoia when you make choices is probably good. And I think when you get older, level of paranoia, you want to decrease level of paranoia because you don't want to change things that often. It's harder to remember the way you drive to work, when it changes a lot when you're older.
In my case, when the question first of all came up, and I said, which ones are the difficult ones? So then I have to think. After I finished grad school, I had job offers mostly from Silicon Valley and other places that do silicon work, but I had already made the decision that I wanted to do something different from silicon, but still related. So Honeywell at that time was doing digital gallium arsenide. They were trying to build a supercomputer based on digital gallium arsenide, and that was they had a computer division at that time, of 4 divisions. So that influenced my decision to go to Honeywell in Minneapolis. 2 months after I got there, Honeywell reorganized. And so
similar stories you'll have here.
Honeywell, well, it wasn't complete. It was still the same digital gallium arsenide, but then they said, okay, we're going to get rid. They sold the division that was supposed to do. I was in corporate research, so I wasn't directly affected. But they sold the division to Boule in France, and which is also gone now. And I'm trying to remember the name of the Japanese company, but essentially they formed another company that was outside Honeywell. So my efforts was directed towards military-related research contracts, in which case for the aircraft aerospace division of Honeywell, so we started supporting that group. And so qualitatively, it did not change the things I did, but it showed you the kind of things that can move on right above you that you don't have much control over. And things still turned out the way I wanted. And my decision at that time was that why I wanted to do Guyana Science, because that was the time of all these 2D gas, and thought that, okay, I'll work in an area that's cool, will be in industry, but maybe I can go to academia later. So that was the decision I made, and it turned out to be good for me because I was able to change projects within Honeywell to other things as Honeywell morphed, but still kept me in line to be able to go to academia when the time came up. Even when I changed projects within Honeywell, I would do exactly what Honeywell wanted to do, but I'll negotiate to get things that will allow me to go to academia.
Thank you. Next question.
With the election coming up, the news is beginning to focus on politics, and I know that you're all pretty involved in politics.
No.
At least in the loop, right? And I find it a little bit disturbing that science is really very poorly represented in the election and politics in general. In fact, not only haven't we had a scientist as a president since, I guess you could say Jefferson, really, but there's also very little discussion of science, even in the election process. And I thought maybe that there's probably even greater separation of science and state than there is church and state. So does this kind of thing bother you? And do you think it should be changed, and how should it be changed?
I'd love to take this one first. You must be watching Fox. I mean, I can, that may be true in the Republican debate. I mean, President Obama is a huge supporter of science. In fact, he's mentioned it in not this past State of the Union so much, but the prior one extensively. In fact, he makes a point to visit schools and talk about science. I mean, we have a Secretary of Energy who is a Nobel Laureate physicist. I mean, and it's key to the sort of, jobs and innovation, and in fact, why the science agencies have all, even in this terrible budget, when the rest of them are shrinking, are all in the President's request, and even Congress have been increasing the budget. So even this year, the debate that's going on about next year's budget, both the House and the Senate have recommended increases in both, at least the NSF and the NIST budget. I don't know if they've talked about NIH yet.
They're not touching basic science.
Yeah. Within the current administration, they're very big supporters of science and talk about it all the time. And when the president signed this recent big bill that changed the patent law, he did it at a science and technology magnet school in Virginia that my daughter goes to. So he's really. So I think what the question really has to do with the fact that within the country, what you're really seeing is, as we all know or hear, is that there's just extremely strong currents still in the United States of anti-intellectualism and that and the sort of geek thing and stuff, and how to fix that is a much more difficult problem. But I think the politics just reflect the culture, honestly.
Yeah, so it's certainly true. PhDs don't seem to run for high offices. I think scientists do not have. I don't know. You guys need to practice your interpersonal skills and public speaking. So maybe we'll have a president with PhD again in the future. But as Lloyd said, I think it's for the very first time the Nobel Prize winner is appointed at the secretary level. So Steve Chu, I don't know how much he enjoys his job, but to his credit, I went to his talk maybe 6 months ago, and so he is a cabinet member, but he still hooks up his laptop by himself, and he actually he gave a scientific talk. So even if you are at this position, somehow science cannot be completely eliminated from your life if you are passionate enough about it. But also, I think, the few professors who, President Obama visited MIT at some point.
Right, yeah.
And people who met with him really said that he's incredibly insightful and clever in terms of questions he can ask. So that, if president can ask good question scientifically, that's already a good start. So I think we should, we should maybe reduce our expectations when it comes to science and politicians. I've been to India 2 years ago, and actually, former president of India is a PhD physicist, and he at the age of, I don't know, I think he's 81 right now. And he actually gave a somewhat scientific talk and talked about nanotechnology and nanoparticles. He read it, but so anyway. But I think overall, as you see, I mean, the funding budgets are not shrinking. I think what the problem is with politics in general, and maybe politics in this country, that depending on administration, things may change. So there is no sense of stability when it comes, to academic environment, and always wondering what will happen 4 years from now. But overall, I think scientific budgets here are still stronger per capita than in many countries. Maybe maybe except emerging countries like China, Singapore, maybe Brazil, where there's enough money that they are able to pump a lot of new money into science. But if you look at Europe, Canada, I think it's still not as good as it.
I take, without focusing on politicians and talking about the government in general, you find a lot of involvement of scientists, even as congressional fellows. Politicians depend on those congressional fellows. Usually they're PhDs from UIUC, from Harvard, who go to Congress to spend 2 years and provide advice. Maybe they're not taking, but they get to know what the process is. They get to know how things are done. I give 2 examples that at least 5 profile. One of the program managers with us at DARPA, she finished a degree at MIT and didn't quite know what she wanted to do, but then she decided to become a congressional fellow, AAA as a fellow. I went to work with Senator Baucus on energy, and she was part of putting together all those energy policies and a lot of the decisions that are made there. So there's a lot of room for contributions by scientists. And though you may not be the face of what's directed, but we can participate in the process and have an input into that.
Well, I don't know what to add. I would stress the fact that I do agree the current administration is a fresh change with respect to what we had previously. I was just coming to this event and I was listening to the radio talking about the policy, about the climate policy, where in the previous administration there were actually people, councillors, suggesting that the global warming is not, and in fact doesn't exist. At least we are not anymore there. So there is a big change. So I hope it will stay this way.
Okay, so we have time for probably one more question. We've got one more question from the audience. I'll ask a try to ask a more fun one. So
Okay.
Great. So we're all graduate students. We work really hard. How many hours did you all work in your graduate school? And is that dependent upon your success level? Is that dependent linearly, inversely on the number of hours spent?
You don't want to know the answer.
I don't know the answer. I do want to know the answer.
You're having an easy time now. You should tell him that.
Yeah, actually, I remember my advisor told me exactly what Kyle just said, that life in graduate school, even you think it's hard, but it's easy because a lot of things are taken care of for you. You don't have to worry about, I mean, in a way you have a singular focus, which is doing research work and graduate with good enough outcome to get a decent job. So when your career progresses, you have to become more and more multitasking, whether you like it or not. You have more people whom you can delegate things to, but
There are more things that can go wrong too.
but more things that can go wrong, yeah. So So, you know, I think each stage of the career has its own benefits and downside. But another thing about graduate school is you know that it will end. So even if you think that you work so hard, once you graduate, A, possibly you will work less hours, and B, you will get paid more per hour when you get it. So there's a lot of things to look forward to. So I think, you know, that actually, it's very pleasant moment when you finish.
So I worked for, my thesis advisor was a relatively new faculty member who was unmarried and was fairly ambitious. And at that time in his career, so he actually, though he had an office, he didn't sit in his office most of the time, except if he had office hours, he actually sat in the graduate student office with the group from 9 in the morning till about 11 o'clock at night, 6.5 days a week. And so it was pretty much an expectation that we generally would be there when he was there. So it was, you know, now, so I would come, I guess I used to describe my graduate experience as I did not have a lot of fun in graduate school, but I had a tremendous education. I finished with, I think I had 14 peer-reviewed publications by the time I was done, and you know, it was great for my career, and I learned a lot, and I certainly learned how to work hard in time, which many times, not that I still work hard now, but it enabled me to be able to do things when I had something new, to focus and, you know, be incredibly efficient and put everything else aside and work really hard. So, not that everyone works that way, everyone should. So one consequence of this in my career, for example, as a manager, is the first thing I ever told people who work for me was, I don't care when you work. You know, so that's right. As long as you're, you know, so I just want to, you know, you should be really productive, and you should be working lots of hours and really hard because you want to be really successful, not because I expect you to work some net of hours or because I'm here or not here, right? So and I think only once I've ever had a postdoc that I think maybe took advantage of that and didn't work very hard. But generally, you know, really the right answer is how hard do you want to work, how much do you want to get done, and how quickly do you want to get out? I hope that's an answer to faculty members' life.
I think overall you're driven by your sense of inquiry, you know, the inquiry or whatever you're working on in grad school, but also by your ambition and what you want to accomplish within the time you're spending in the same environment. But I found, you know, grad school there were a lot of very bright people that really made the place a conducive place to work. Too many late nights in the lab, and there'll be a lot of people running around, actually working on stuff. I learned a lot more from those graduate students that we work together. And because, you know, there are things that, you know, that are not in the classroom, but also there are things that are things that you can instantaneously learn from each other's errors and mistakes, and those are the best kind of knowledge. So it was an environment that made it look like it didn't matter how much time I spent there.
Right, we go to these phases of life, and I think that graduate school is a very special period, and so you should try to treasure it, because then you will not have the experience again or the same opportunities to focus on a problem or on a group of problems 24 hours a day. At the same time, the freedom even to work on it. Just because you start a career or you work in a different environment, and then you are pulled and pushed left and right, and so you don't have anymore that type of the type of freedom, in a sense.
So I think we're getting the impression that it's all downhill after you graduate.
All right, well, let's thank the panelists and all of you all for the great questions.